Picture this. An astronaut's visor cracks open. No suit, no air, just space. If you grew up on movies, you already know what happens next, right? Boom. Body explodes, blood boils, eyeballs pop out like champagne corks, roll credits. Except, none of that happens. Not one bit of it. What actually happens to your body in the vacuum of space is way weirder, way more brutal in a slow, quiet way, and honestly, way more terrifying than any movie explosion, because it's real. NASA has real data on this. There are real cases of people surviving vacuum exposure, and by the end of this video, you're gonna know exactly how long you'd stay conscious, what would actually happen to your skin, your blood, your lungs, second by second, if you got sucked out an airlock right now. So stick around, because that Hollywood explosion, total myth, and the truth is stranger than fiction. Let's talk about why we all believe this explosion thing in the first place. Every sci-fi movie needs a dramatic death, right? So Hollywood gives us the exploding astronaut. Skin bursting, blood spraying everywhere, the whole 9 yards. It's visually terrifying, it sells tickets, and it has absolutely nothing to do with real physics. Here's the thing. People forget. Your body isn't a balloon. It's not full of pressurized air just waiting to pop the second you step outside. Your body is mostly water and tissue and bone, and it's held together by something way stronger than you'd think. So before we get into the gnarly stuff, and trust me, it gets gnarly, we need 15 seconds of actual physics. I promise I'll make it quick and painless. Okay, real talk. Right now, as you're sitting there watching this, the air around you is pushing on your body with a pressure of about 14.7 pounds per square inch. That's 1 atmosphere. You don't feel it because it's pushing on you from every direction equally. Front, back, sides, top, bottom. It cancels itself out. Now imagine you get yeeted into space. That outside pressure doesn't go down a little. It goes to basically zero. Nothing. Void. So the difference your body actually has to deal with, from the inside pushing out versus the vacuum outside, is just that 1 atmosphere. That's it. That's the whole pressure gap. And here's a fun comparison. Scuba divers deal with way bigger pressure swings than that every single time they dive, and their bodies don't explode. Not even close. So if 1 atmosphere isn't enough to blow up a scuba diver, why would it blow up an astronaut? Short answer, it wouldn't. And here's the science that proves it. This part genuinely shocked me when I found it. Scientists have actually tested human skin in labs. Real cadaver skin, pulled and stretched until it tears, to measure exactly how strong it is. And the number they found is wild. Human skin can handle roughly 27 megapascals of pressure before it rips. 27. You know how much pressure a vacuum puts on your skin? About 0.1 megapascals. Let that sink in. Your skin is over 260 times stronger than what a vacuum could ever throw at it. 260 times. Scientists even calculated what it would actually take to physically blow through human skin using raw air pressure alone. You'd need wind moving at around Mach 4.45. That's over 3,400 miles per hour, faster than most fighter jets. That's the kind of force it would take to literally blast through your skin like tissue paper. A vacuum doesn't even come close to that, not in the same universe. So here's what actually happens to your body instead. And this is where it gets freaky. You would swell up, like noticeably. Gas and fluid trapped under your skin start expanding because there's nothing pushing back on them anymore. Early Soviet and American test animals exposed to vacuum conditions actually puffed up so much, scientists described them as looking like an inflated goatskin bag. Your skin stretches like a wetsuit 2 sizes too small, but it does not burst. It holds, every single time. Okay, skin's not the problem. So what actually gets you? Let's talk about your blood, because this next part is where the boiling blood myth either gets confirmed or destroyed. So here's the thing about boiling. Boiling isn't just about heat, it's about pressure too. Water boils at 212 degrees Fahrenheit at sea level, but take that same water up to the top of a mountain, where the air pressure is lower, and it'll boil at a much lower temperature. Less pressure equals easier boiling. That's just how liquids work. Now go all the way up to about 62,000 feet. Scientists actually named this altitude the Armstrong limit, and the pressure drops so low that water starts boiling at just 98.6 degrees, which, by total coincidence, is exactly your normal body temperature. So in a vacuum, where pressure is basically zero, any liquid touching the outside world instantly T. So in a vacuum, where pressure is basically zero, any liquid touching the outside world instantly turns to vapor. Saliva on your tongue, gone, vaporized. Tears in your eyes, gone. Moisture in your lungs, gone. Sounds like blood should boil too, right? Here's the twist. It doesn't. And the reason is honestly kind of beautiful engineering, courtesy of your own heart. Your cardiovascular system isn't just some open bag of liquid. It's a closed, pressurized loop. Your heart is actively pumping and squeezing blood through your veins and arteries with real, measurable pressure. That's literally what blood pressure means. As long as your heart keeps beating, the pressure inside your vessels stays way above that boiling threshold. Your blood is sealed off from the vacuum completely, like a submarine hull holding back the ocean. So no, your blood will not boil in space, not while your heart's still beating. But, and this is the part nobody tells you, the second your heart stops. It's a totally different story. We'll come back to that. For now, let's talk about the real killer, the thing that actually takes you down first. And spoiler, it's not explosions and it's not boiling. It's something way sneakier. Alright, this is the part you clicked for. How long would you actually survive? The real killer in a vacuum isn't mechanical, it's oxygen. Here's what happens. Normally your lungs are basically an air pump. Oxygen from the atmosphere pushes into your blood because there's more oxygen pressure outside your lungs than inside. That pressure difference is literally how breathing works. In a vacuum, that pressure difference flips instantly. There's zero pressure outside now, so oxygen doesn't push into your blood anymore. It gets pulled out of your blood, back into your lungs, and straight out into space. Your lungs go from an oxygen pump to an oxygen vacuum cleaner in less than a second. That freshly deoxygenated blood gets pumped straight from your heart to your brain. And that trip, it only takes about 10 seconds. So here's your actual timeline, and I want you to really sit with these numbers. You have somewhere between 9 and 15 seconds of what scientists call useful consciousness. That means 9 to 15 seconds where you could still think clearly, still make a decision, still try to save yourself. After that, lights out. You black out completely. About 30 seconds in, your body goes into full paralysis, sometimes violent convulsions, and without help, brain death follows within a couple of minutes, 9 seconds. That's basically the time it takes to read this sentence out loud. That's how fast space turns from I'm fine to I'm unconscious. But, and this is honestly the wildest part of this whole video, there is a survivable window in there. There are real documented cases of people getting exposed to near vacuum conditions and living to tell the story. Let's talk about what actually happened to them. This isn't just theory, this has actually happened. There have been real depressurization incidents in test chambers, in near space accidents, where people got exposed to vacuum or near vacuum conditions for several seconds and survived. In documented cases, people reported the exact sensation you'd expect from what we just talked about. The moisture on their tongue boiling away, a strange fizzing feeling under their skin, and then the lights going out. Fast. The people who lived did not die from explosion. They didn't die from boiling blood. They lost consciousness from oxygen loss, and they were saved because someone got them back into pressure within that critical window, before permanent brain damage set in. That's the real horror of it, honestly. It's not instant and gory like the movies show you. It's fast, it's quiet, and it's a race against a 10-second clock. But there's one more danger here that's honestly just as scary, and it happens before you even get exposed to a full vacuum. It's the danger of decompression itself. And this is the part where holding your breath, the thing your body is screaming at you to do, could actually kill you first. Here's a rule from actual aerospace medicine that sounds completely backwards. If you're ever caught in a sudden decompression, the worst thing you can possibly do is hold your breath. This comes down to something called Boyle's Law. Basically, gas expands like crazy when pressure drops. So if you hold your breath and seal your airway shut, the air already inside your lungs starts expanding rapidly with nowhere to go. Your lungs are not built for that kind of internal pressure. The tiny air sacs inside them, called alveoli, will straight up rupture. That can cause your lung to collapse, or worse, force air bubbles directly into your bloodstream, which can travel to your brain or your heart and cause an instant stroke or cardiac arrest. So the golden rule, the one thing that could genuinely save your life in a real decompression event, is this. Exhale. Force the air out. Keep your airway open. Don't fight it. Don't hold it in. Let it go. It's the most counterintuitive survival advice in the book. Every instinct in your body tells you to hold your breath in an emergency. In space, that instinct will kill you. And even if you survive the initial blast of decompression by exhaling properly, there's still one more slow-motion disaster creeping up on your body from the inside. This is where we circle back to that heart-stopping thing I mentioned earlier. Remember how I said your blood stays liquid as long as your heart is beating? Here's where that promise runs out. As oxygen deprivation drags on and your body starts shutting down, your blood pressure starts crashing, especially in your veins, which run at way lower pressure than your arteries to begin with. Once that pressure drops below that critical boiling threshold we talked about earlier, tiny gas bubbles genuinely start forming inside your veins. Those bubbles travel toward your heart, and they build up inside the heart's chambers. Now your heart is trying to pump gas bubbles instead of liquid blood, and gas doesn't pump the same way liquid does. Doctors call this vapor lock, and it's basically your heart's pumping motion going completely useless even while it's still physically moving. That's the true final stage. Not an explosion, not a bang. A slow, silent mechanical failure, one system shutting off after another like a ship losing power deck by deck. So let's bring this all the way back around. Your body would not explode in space. Your skin is over 260 times stronger than it needs to be to survive that pressure difference. Your blood would not instantly boil because your own heart keeps it under pressure. What actually gets you is oxygen, leaving your blood in under a second and taking your consciousness with it in under 15. And somehow, that's scarier than any explosion Hollywood could ever animate. Because it's real, it's quiet, and it's happened to real people who lived to describe exactly what it felt like. Space isn't going to make you pop like a balloon. It's going to switch your lights off, fast, silent, and with a clock that gives you less time than it took you to read this sentence. If this blew your mind, hit that like button, subscribe if you're new here, and drop a comment. Would you have guessed the explosion thing was a myth? I'll see you in the next one.